Hi, I'm long, as in not short, long, just long. I'm an AP chemistry student in somebody's AP chemistry class. I'm here to fill in for him since I have absolutely every intention not to disappoint him, but perhaps to disappoint myself. Okay guys, we need to finish off the chapter 10, so I'm going to go really fast. Vapor pressure, okay, think about vaporization going from liquid to gas at a boiling point, and evaporation is changing liquid to gas below the boiling point. So we have, let's heat or enthalpy. Think enthalpy is the heat content of vaporization. And what that is, that's what this is right here. It's the energy required to vaporize 1 mole of something at 1 atmosphere pressure. That's the key thing to look at. All right. The vapor pressure, you'll have to see the video with the water bottle and the infrared lamp. Okay. Now remember, vaporization, it's an endothermic process. It does need heat. And why? Because energy is required to overcome those intermolecular forces. That's a key thing, and this is responsible for the cool earth that we have. It takes a while. When you look at water, it takes a while for water to be overcome, to go from a liquid to a gas. It takes a lot of heat energy. This is also why we sweat, which you never let them see you sweat at all, especially, for some people. All right, let's move on. Condensation is the opposite. You're going from gas to a liquid. In other words, in condensation, there is a dynamic equilibrium with vaporization in a closed system. Okay, so what do you mean by dynamic equilibrium? How fast it evaporates and how fast it condenses or condensates, it's the same rate. That's a dynamic equilibrium, okay? So when we look at a closed system, you can't have something go in or out like a flask or maybe a bottle with an infrared lamp. That would be an example of a closed system. Here we put a cork in it. Now what the heck is a dynamic equilibrium? Okay. When first sealed, the molecules will gradually escape the surface of the liquid. Not a big surprise. We do expect that to happen. As the molecules build up above the liquid, some of those molecules will condense to go back into the liquid. Okay, so you've got some molecules that escape from the surface going from liquid to gas, but it doesn't stay that way. Okay, so what's happening is that the gas molecules will now start coming together as they lose that heat energy. They come together and they form condensation, and it's going back down into the liquid. As time goes by, the rate of vaporization remains the same, but the rate of condensation increases because there are more molecules to condense. Okay? Now, if you think about it, you keep having more stuff going up here at the same speed, but what happens is there's more and more condensation happening because you've got more molecules now that are going to lose their energy and they're going to condense. So you've got this thing going back and forth. It's not necessarily at the same speed, which in chapter 12 we're going to look at reaction rates. This is not a reaction rate. This is merely a phase change. That's all that it is. Okay? So with that, if you notice with the slides, we just add more and more pieces to the puzzle. That equilibrium is reached. When is it reached? When the rate of vaporization is equal to the rate of condensation. The molecules are constantly changing phase. They're dynamic. It is like our planet. Our planet is dynamic. It's constantly changing. It's like us. Our bodies are constantly changing. We always have things happening. That's where the dynamic comes in. Now, the total amount of liquid and vapor remains constant. That's when you get the equilibrium. Hence, the idea of dynamic equilibrium. Okay? Rate of vaporization is equal to the rate of condensation. Molecules are constantly changing. Okay, phase, that's dynamic. And then the total amount of liquid and vapor remains constant. That's the equilibrium. All right. Any questions? That's gotcha. I'm long, by the by. Vapor pressure. So the vapor pressure is the pressure above the liquid at equilibrium. Okay? Liquids with high vapor pressures evaporate easily. They are called volatile. Okay, so when you hear the word volatile, that means it's going to evaporate fairly easily. What are good examples of liquids that are volatile? Water is not that volatile, but many alcohols are. They do evaporate fairly easily. Now, are we talking about adding heat to this? No, just looking at it at room temperature. You guys know that rubbing alcohol, it evaporates fairly quickly. It doesn't stay. That's pretty volatile, okay? Same thing with fingernail polish remover. It doesn't stick around because you have acetone in there. Acetone is another solvent similar to water, okay, but they use that in fingernail polish remover. That evaporates fairly quickly. That makes it volatile, okay? Now, it decreases with increasing intermolecular forces. So in other words, the more IMF that you have, the harder it is to go and evaporate. You also have bigger molecules. You get bigger London dispersion forces, but you also have more polar molecules. That also decreases that volatility, that dipole-dipole. It does make it harder to do it. So vapor pressure also increases with increasing temperature, and we can measure that pretty easily with a barometer. So we can check out air pressure using a barometer, okay? And this is the one that was done by Torricelli. You guys might remember him. He took a tube of mercury, sealed it off, and he filled it up that there was no air in here. And what he did, he had a bowl of mercury, went down to the beach, measured it, and he noticed that the column was 760 millimeters high at the beach, which we set it at 1 atmosphere. Okay? When he went up into the mountains, what would we expect for the column to do? Would it go up, down, or stay the same? Long, you said it was going up? Bradley, you said it was going to go up? Oh, Sean? You're saying it's down? Nathan, you're saying it's down? Mia, you're saying down? Hey, Kevin, how about you? Down? Okay. All right. Awesome. Awesome. It is, in fact, going down because there's less air pressure pushing down on this to force the mercury to rise up. So, that being said, that's the whole point. And remember, if you did get the answer wrong, don't feel too badly. Everybody's here to learn. Let's move on. So, if we inject a volatile liquid in the barometer, it will rise to the top of the mercury, okay, and there it will vaporize and push the column of mercury down. So this is if you're doing something a little bit different than the original experiment. So they used water here for that, okay? So the mercury is pushed down by the vapor pressure. So this is one, and why in the world would we go do something like this? Okay, because this is a way of measuring the vapor pressure of gases. Okay, so what I mentioned to you earlier, and I was asking you guys the questions, that was just plain old air. If you inject something that's volatile, like water, water can evaporate. Okay, it's just alcohols are easier to do that. All right. So the mercury gets pushed down by the vapor pressure down to 736 millimeters of mercury. So our atmosphere is equal to the pressure of the mercury plus the pressure of the vapor. So thus the pressure of the atmosphere minus the pressure of the mercury gives us the pressure of the vapor, and that's how we can find out the vapor pressure of a liquid at a certain temperature, effectively at sea level. Okay? Let's move on. The temperature effect. If we look at the number of molecules and we look at the kinetic energy, there is a certain amount of energy that's needed to overcome the molecular forces. Of course, the more molecules you have, the more of this kinetic energy you're going to need. Okay? That's the idea. But if we look here, if you have a higher temperature, more molecules have enough energy minus the higher. That means more molecules have enough energy, thus you have a higher vapor pressure. Okay, now it's the energy needed to overcome those intermolecular forces. So when you look at it at a different temperature, okay, when you're looking at it at a different temperature, then the amount of your higher vapor pressure, lower vapor pressure, that temperature is definitely a factor in there. Okay, so going back, here's temperature 1. You need this amount of energy to overcome the intermolecular forces to get them to go volatile on you. When you have the temperature that is higher, which is what we have here, you actually need a little bit more energy to make it harder and to make it work. Okay, and you notice that the shifting of the curve, it's now shifting a little bit more this way because you need to put in more energy in there. All right. Mathematical relationship, we're not going to worry about the mathematical relationship for this. Delta H vaporization is the heat of vaporization in joules per mole. Okay. We do need R. Okay, R is 8.3145 joules per Kelvin times mole. That they would give you the constant for that. Okay. Moving on, changes of state. The graph of temperature versus heat applied is called a heating curve. Okay, the temperature of a solid turning to a liquid is the melting point, and the heat required to accomplish this change is called the heat or enthalpy of fusion. There's the heat of vaporization, which is still delta H, that's also enthalpy. Remember, enthalpy is the total energy involved. So you have the heat or enthalpy of vaporization. What's the energy required to go from a liquid to a gas? When it's fusion, it's the energy required to go from a solid to a liquid at the melting point. That's the thing, okay? Now, when you look here, when you look at this is a temperature energy diagram, and let's say we're going to do this of water, you'll notice that you have the different phase changes in there. So right here, this is ice, okay? But when you're looking here, this is also ice going toward water, liquid water, but the temperature is the same, okay? The temperature is the same. Then, once you are here, this is liquid water going toward the gas stage. Okay? But there's a certain point, it's going, and so now it's melting, melting, melting. Okay, let me rephrase this. Let me try this again. I'm sorry, I made a mistake. I'm going back here. So this is all ice, 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 ice. Temperature doesn't change. You have to put enough energy to make it happen. And then what's happening is it's going from ice to liquid. So this is still ice here. This is going from ice to liquid. Now, this is all liquid, but it's going on its way to gas. But you may notice that the temperature does not change. That's because you were building up the energy. Once you go here, then that's gas. That becomes the water vapor. Okay? All right. Of course. That would have been too easy. I'm Long. Just remember that name. All right. Melting point. Okay, that's determined by the vapor pressure of the solid and the liquid. At the melting point, the vapor pressure of the solid is equal to the vapor pressure of the liquid. Okay, if you notice, I'm kind of going fast here. So, here's the diagram where you have liquid water, solid water, okay, and you have water vapor. So,
if the vapor pressure of the solid is higher than that of the liquid, the solid is going to release molecules in order to achieve the equilibrium. What do you mean? The equilibrium between condensating and freezing, okay? I mean, the difference between melting and freezing, not condensating, because it involves a gas, while the molecules condense to a liquid, okay? This can only happen at the temperatures above the freezing point since the solid is turning into a liquid. Like I said, we're going rapidly. When the vapor pressure of the liquid is greater than the vapor pressure of the solid, what happens? The liquid now releases molecules to achieve an equilibrium, okay? While the molecules condense to a solid, in other words, they start to freeze. The temperature must be greater than the freezing point, okay, since the liquid is turning to a solid, and the vapor pressure of the solid is equal to the vapor pressure of the liquid. They're condensing and vaporizing at the same rate, the solid and liquid, and that's when we find the melting point. Okay, boiling point, as we finish off, reached when the vapor pressure is equal to the external pressure. Normal boiling point is the boiling point at 1 atmosphere pressure. Superheating is heating above the boiling point. Supercooling is cooling below the freezing point. Okay, 78 and 79 phase diagrams that will not be on the AP exam, so I am not going to worry about it. But this is just telling you the pressure and temperature at what state that the water is in this case. But you are not going to be needing this for the AP exam, okay? Don't worry about slide number 78 and 79. Don't. I'm not testing you on it either, okay? All right. I hope this benefited you guys, and don't forget, my name is Long. Bye.